Okay, and this is the C4, C5, C6 walking talking mock. First thing to note is that on the inside front cover of the chemistry one, you will get your data sheet which tells you about how we test for different ions. So that's given, don't have to remember anything. And on the final page, or the inside final page, is the periodic table. So again, get quite a lot of information from this one, make sure you use it when it's needed. Okay, so we look at this. Okay, we've got Jack writing down some data about some elements of group 7. Jack has made a mistake, so we've got to identify that mistake. It says one of the boiling points is wrong, which boiling point in the table is wrong, and explain it. So we're going to get a mark essentially for a statement and an explanation, which is okay. So we have a look. I mean, the first thing I do is just make sure we're using the right part of the table. Because it's a group, it should have a pattern. So we identify the one that's not in the pattern and then say something towards that effect. Just being specific, don't just say it does not fit the pattern, try and explain what it should be or why it's not the right answer, why it's not a correct value. Then it says estimate the correct value for the boiling point. So we've just got to give something, and it's presumably going to have a large range. Okay, so you kind of got to look at the pattern of the others, and then it's an estimate, but they'll always give you a fair number either way. Acidity is another element in group 7 of the periodic table. What's the formula for a molecule of acidity? Well, we've got the formula here, and we know that we can look in the periodic table for acidity. Okay, so we should be able to use that information, this information, to figure that out. So there's nothing there that really requires any knowledge at all. It's all given in the table or on the periodic table. So nothing difficult there. On those questions where you get all that information, please make sure you use it. Next one, we've got a table showing some information about the element hydrogen, and we've got various things. So we've got the state at room temperature, type of element, atomic number, number of electrons in outer shell, maximum number of electrons the shell can hold, etc. Ion, formula of chloride, reactivity. Okay, so we've got a lot there. Now the question is this: is Faye and Guy are discussing where hydrogen fits in the periodic table. Faye is suggesting it should be placed in group 1, as it sometimes is on periodic tables, and Guy is thinking it doesn't fit into group 1, it should be on its own. So use information in the table and your knowledge of group 1 elements to evaluate the ideas of Faye and Guy. So I think this is the key thing. Okay, so we want to say, I think probably, what parts of Faye's work and what parts of Guy's work. So we'd probably split our answer roughly. And then what we've really got to do is go back to the table, and this is a bit annoying that it's placed on another page. So hydrogen is similar to group 1 elements, so we've got to identify the things where it would be similar to group 1 elements. So for example, this one, okay, number of electrons in the outer shell of an atom, or this one, or this one. Sorry, they should be the same colour as there. So then we'd talk about them and we'd try and explain why they agree with Faye. Okay, so the properties of group 1 and how that links to what Faye says. Okay, and then we'd try and talk about some properties of group 1 and say about why Guy's right. So essentially we're just splitting the answer, as often we do, into 2 parts. It's not necessarily more complicated than that, because again, a lot of the information is given, but you need to know the properties of group 1 elements and you need to remember them. Next one, hydrogen gas reacts with lithium at high temperature to make lithium hydride. At the high temperatures of the reaction, lithium is a liquid and lithium hydride is a solid. So giving you some information there. Now, because it's in balls, we're going to have to use it. The equation shows the reaction of lithium with hydrogen. Fill in the missing state symbols and balance the equation for the reaction. The state symbols should match the state of the chemicals at the high temperatures of this reaction. So, i.e. this. Because lithium is usually, well, at room temperature it would be a solid. So, probably the first thing to do is to put in the state symbols. Okay, so this should be fairly obvious. They go in here, and here, and here. And remember, the state symbols we can use are AQ, solid, liquid, or gas. And probably the second thing to do, maybe a little bit harder, is to balance the equation. Now, even though it doesn't give you any working out space, there is nothing stopping you using this area or this area to kind of use to kind of work it out. I mean, this one looks relatively straightforward, so it probably won't take too much working, but nothing's stopping you using a bit of extra space, work it out, get it sorted, make sure you've got the same number of atoms of each element on either side. Next one, formula for lithium hydride is LiH. Lithium ions have a charge of +1. What is the formula of a hydride ion? Right, so okay, now this is going to be a bit unusual. This is really a bit of a trick question, because often hydrogen does have a charge of H+. And if we've done about acids, we'll know that acids dissociate to form H+ ions. In this case, lithium has a charge of +1. So if that was the case, if it was LiH, both had plus charge, it would be LiH2+, which wouldn't really be a thing. So it's got to be something different to that. So we'd probably get rid of any of these positives, and then we'd have to choose something that seems reasonable from the negatives. Remember, we want to make the charges overall equal out. Then another compound has the formula CaH2. What is the name of this compound? Well, we've been told earlier on the name for LiH is lithium hydride. So it's not really a jump to figure out what CaH2 is. Next question. Arsenic can be used to treat some cancers. Okay, arsenic, some cancers. Ben wants to analyse a mineral to see if it contains arsenic, so he wants to analyse it. He looks at a table of flame colours for some elements. Okay, so you've probably done the flame tests for elements, and you'll see these different colours. And you'll notice arsenic's blue, and I haven't read anything else, but I'm just going to make a note that copper's also blue. Ben talks about what a flame test could show. I can use these flame colours to show that there is no calcium or sodium in the mineral. The flame colour will not prove that the mineral contains arsenic. Okay, so no calcium or sodium, and it will not prove, and that's crucial, the mineral is arsenic. I'm just going to make a little note of that. Explain why what Ben says is true. So again, with these questions, he's got two statements. So I'd probably start with this one. Okay. So it will not prove that the mineral contains arsenic. So we'd look back up at our table. Now remember, we made a note that copper's also blue, and we'd use that idea to help us. Then we'd think about calcium or sodium. So if they were present, would get a red or yellow colour. So if there's no calcium or sodium, if there's no red or yellow colour, it should show that that's not present. And then we have a lined spectrum of arsenic. Okay, so we've got the diagram. And Ben says, I will take a line spectrum from the mineral. I expect it to show that the mineral contains arsenic and other elements. How can Ben use a line spectrum to show that the mineral contains arsenic and other elements? So, what would we want them to think there is, if that's arsenic, what we'd expect to see is if you take your flame, if you take your spectrum of this mineral, well, we'd expect to see if it contains arsenic, lines in the same place. This is my impression of what's going on there. But we'd also, if it was a mineral and if it contained elements other than arsenic, it would contain lines in other places, which would mean it contains something else, not just arsenic. Tricky question, that one. It's just trying to explain the idea of line spectra, nothing more than that. Ben finds out that arsenic is in group 5 of the periodic table. Some arsenic atoms have different atomic structures to other arsenic atoms, and we've got the information about 2 different arsenic atoms. Okay, so we've got arsenic 75 and arsenic 73. How does the table show that the 2 atoms are the same element? Put a tick in the box next to the correct answer. So, same element, that's the crucial thing. And we look at these and we try and eliminate things if we don't know. I mean, some of you might know straight away. So, first one, both atoms have similar relative atomic mass as well. That definitely doesn't help us. So we get rid of that one. Arsenic 75 has 2 neutrons more than arsenic 73. Well, that's not a wrong statement, but does it help us in any way? Both atoms have the same number of protons, okay, and the number of electron shells is the same. Well, there'll be other elements with the same number of electron shells, but there won't be other elements with the same number of protons. So we can pretty confidently go with this one because it's got the same number of protons, and the proton number determines the elements. Right, and now moving on to C5. We've got properties of diamond and graphite. Diamond, graphite. And we've got various properties, very similar melting points, identical boiling points, both insoluble. We've got some differences here in the electrical conductivity and the hardness. So Sam notices that some of the properties are similar and some are different. Finds diagrams that shows the structure of diamond and graphite, so they've given you some nice pictures, which is very kind of them. And what you've got to do, again, question over the side, annoying. The table shows some similarities and differences in the properties of diamond and graphite. Use ideas about their structure to explain these similarities and differences. So, what we'd want to be doing is we'd want to look at a couple of similarities, maybe, and a couple of differences, and then we'd want to try and explain it using ideas about their structure. Okay, so it might be that we choose a difference as electrical conductivity. Now, we can explain this using the idea of free electrons, so that's what we'll probably do, and that's then linking the idea of structure to a property. We could explain the difference in hardness. And we could compare the structures to talk about layers in graphite. In fact, it's only got 3 bonds, whereas in diamond it has 4 covalent bonds between each carbon atom. And then we might talk about a similarity. So if we go back up, well, we could choose melting point or boiling point or solubility. I think maybe melting point and boiling point, both very high. Okay, so therefore we'll talk about, you know, strong covalent bonds and the energy needed to overcome those covalent bonds, that kind of thing. The crucial thing is this with this question is we get in as much as we can about their structures to help explain these similarities and differences, but we really want to be talking about the structures, and we must cover a similarity and a difference. But it was only targeted up to grade C, so we're probably not going to be stretched too much there. Then we've got Zoe working for a mining company, extracting copper from 2 different minerals. So they've got cuprite and chalcocite, different formula. Zoe works out percentage of copper in cuprite. Okay, 88.8%. She uses this formula, so they give you the formula. Brilliant. Calculate the percentage mass of copper in chalcocite. Give your answer to 3 significant figures. It's worth 3 marks, which is crazy for a question like this. So, quite a complicated way of stating the equation. So, total mass of copper in gram formula mass divided by gram formula mass of compound, or pretty easy, where Cu2 divided by Cu2S, and it just wants to be the relative formula mass. They've called it gram formula, so they're actually giving it values of grams, and that means we can then use it to work this out. Okay, so it's just the relative formula mass divided by the relative formula mass of that times 100. And then you've just got to make sure it's 3 significant figures, and you get 3 marks for that, not difficult. Then use your answer to work out how much copper can be extracted from 1 kilogram of pure chalcocite. Well, let's say for example it was 90%. Well, from 1 kilogram would be able to extract 0.9 kilograms of chalcocite, but we need to know this value from here. So it would just be expressed in a percentage as a decimal. The minerals are transported from the mine to be processed to make copper, so he thinks about the environmental harm caused by transporting each mineral. I think we should use minerals with higher percentages of copper. Transporting these minerals causes less environmental harm. Okay, high percentage of copper. So transporting these minerals uses less environmental harm. Do you agree with Zoe? Well, yeah, we probably do. So why would using minerals with a high percentage of copper, why would transporting them cause less environmental harm? Well, let's imagine we've got one with 5% copper and one with 90% copper. We still need to transport the same amount of copper, but this one's going to be transporting much more other materials than this one, and we've got to try and relate that to environmental harm. Now when it talks about environmental harm, please don't just talk about pollution. you can mention the word pollution, but you've got to be specific. So to me, if I'm answering a question like this, I'd be talking about things like energy needed or fuel needed to transport, and then I'd be talking about CO2 or maybe some of the other gases you learned about when you were doing C1, so nitrogen oxide, sulfur dioxide. Okay. Next one, atmosphere of some planets. Okay, so it's planet atmospheres. Other planets do not have the same atmosphere as Earth. Okay, yeah. Venus has an atmosphere that is mainly carbon dioxide with about 4% nitrogen. The atmosphere on Jupiter is mainly hydrogen with about 10% helium. The atmospheres on both planets contain very small amounts of gases. Using the gases named in the information, complete the table below. A gas whose molecules have a relative formula mass of 2. Well, where are we going to go for that? We're going to go for our periodic table, if we don't already know it. A gas that is a compound. Now, it's crucial that you use the gases named in the information. So you could give, I don't know, methane, for example. You wouldn't get that right though, because it's got to be ones that are in this information. A gas that consists of single atoms. Well, single atoms, they're from noble gases or group 0. So again, I'm going to be using our periodic table to check that out. Next, the atmospheres contain molecular substances. What are the properties of molecular substances? Put ticks in the boxes next to the 2 correct answers. So, molecules. Alright, things like carbon dioxide molecule, hydrogen gas, oxygen gas, water, etc. Okay, so do not conduct electricity. Well, if we think about those things, they don't, so that would be reasonable. They all have boiling points above room temperature. Well, that would mean they were solid at room temperature. Form crystals at room temperature? Nope, doesn't look like it. They have low melting points. Yeah, if you look at all those, they're gases or liquids. They're hard and strong. No. Quite easy, that one. The atoms in a hydrogen molecule are held together by a covalent bond. Which statements are true for the hydrogen molecule? Right, okay, so we'll have a look through. This one might be a bit harder. Okay, so if we imagine we've got hydrogen. That's something like that, covalently bonded. Put ticks in the box next to the correct answers. The nuclei of the 2 atoms are attracted together. So we've got to think, what charges are in a nuclei, and that is positive. Would they attract? Electrons attracted together to form a bond. Again, I've got to think electrons. What charge do they have? Negative. Are they going to attract? The nuclei of the 2 atoms repel each other. Well, that's a correct statement. Yeah, because nuclei do repel each other. The nucleus of each atom attracts the shared electrons. Well, the nucleus contains protons, which are positive, and the electrons are negative, so that one might work. And the electrons repel the nuclei away from each other. Well, the electrons wouldn't do that, that would be the nuclei themselves repelling. So we should be able to figure that one out. And then on to C6. And we've got Alex adding dilute hydrochloric acid to solid sodium carbonate, calcium carbonate. He sees that a reaction makes bubbles of gas. I mean, really, yeah. Okay. It's a good thing he's wearing those safety specs. Complete the word and symbol equation for the reaction by filling in the boxes. Okay, tricky-ish question. So it requires us to remember our general equations. And what we've got here is a metal carbonate and an acid. And we should be able to remember that makes a salt, symbol form of which is given. It makes water, and it makes carbon dioxide. Okay, so we should be able to fill that in, and then the only difficult thing really is to say what that's called and give the correct formula for calcium carbonate. But remember our trick for this. We've only got to remember a few things. Carbonate is Ca3+, that's one we do have to remember. Calcium is in group 2 of the periodic table, so we should be able to think of what charge it has and then build those two ions together to make the compound. Rate of reaction. So Alex predicts the more concentrated the acid, the faster the reaction. Okay, yeah. Plans some experiments to find out if his prediction is right. He has this equipment, so he's got a gas syringe, conical flask, and his reaction mixture. And he's got 3 different concentrations. So 20 grams per decimeter cubed, 10 grams per decimeter cubed, 5 grams per decimeter cubed. Describe how Alex can use the equipment and his results to show that the more concentrated acid, the faster the reaction. Okay, so got to describe how you can use this equipment and his results. So firstly we'd go with the equipment and method. Okay, so equipment and method, and then we'd talk about his results. So for the equipment and method, would we want to be thinking about kind of writing a little basic method. So what you could do, oops, should be in yellow. So we're talking about things like measuring gas produced or volume of gas produced. In a set time. And then, because they're talking about how you can use equipment, we might want to talk about things like control variables and repeats, all the usual things that we'd talk about. Okay, so that the equipment, we're basically trying to say how he's going to use the equipment, which is a method and control variables. And then when it comes to the results, what can you do? Okay, so well, the higher the time, would that be a faster or slower reaction? Higher time it takes for, say, a certain amount of gas to be produced. If we could plot a graph, and again, you know, which one would be the one that's more concentrated? Okay, so fairly straightforward. Questions targeted up to B, that one. Then we go, the results of the experiment in part B confirm that the reaction is faster with more concentrated acid. Why does this happen? Again, ticks in the boxes, and it's 2 correct answers. Okay. More concentrated acids have larger acid particles. Well, that's nonsense. At high concentrations there are more particles in the same volume. Well, it seems reasonable. Correlation rate increases when particles are closer together. Oh, yeah, if you're packed closer together, you're more likely to hit something else. High concentrations of acids split the calcium carbonate to give a bigger surface area. I don't understand how that happened. And reactions are faster when particles have less energy. Well, that's again an obviously wrong one. So we've excluded 2 that are obviously wrong. And another one that's pretty much wrong. Ooh, is that 2 pages? Not 1 page. Blank page. And then we get a titration question. So some students do titrations to find out the concentration of acid and vinegar. We've got the equipment they use, and you can see we've got sodium hydroxide up here, the alkali, and acid down here, which is vinegar, at an indicator. Titrations always occur between acid and alkali. There's always an indicator to tell us when a certain point has been reached, what we should call the end point. Each student does a first titration, then repeats the titration several times. Calculate an average result from their repeats. First titration result is not used to calculate the average. Why? Okay, so we've got 4 choices here. Okay, now these are often the hardest ones from Mercy Art. It wants it next to the best answer. So some of these aren't necessarily wrong. The first result is usually lower than the others. Well, probably it might be, it might not be. Depends. First titration is done without an indicator. Well, no, we'd never do it without an indicator. Students do not follow the method carefully the first time. Well, that's possible. The first method result is used to give a rough idea of the volume needed. So we'd have to choose between which is the best out of those 2, and hopefully we should come to the right one. All students test vinegar from the same bottle and use the same concentration of sodium hydroxide. Okay, the students record their average results in a table. Okay, so looking through them, to me, that one comes out straight away. The others are reasonably close. The students notice that D's result is very different from the others. They suggest explanations for this. So, Amy, Ben and Carl, I mean, Ben's a right clever one. He's been having a go at people all the way through. Amy, I think she must have gone past the end point. Ben, the vinegar she tested is more concentrated than the others. Carl, she made mistakes when she measured the volume of the vinegar. So, if we go back, well, let's read the information carefully. So all students test vinegar from the same bottle is one of our things. So, what's it asking us to do? Which student has the best explanation for D's result? Explain why you agree or disagree with the ideas suggested by the other students. Okay, so this one requires a little bit of thinking and cross-checking with the table. So the first thing we notice is that D's result is lower than the others, and that's important. Okay. So if Amy's right, she must have gone past the end point. What we'd expect is that one to be higher, maybe something like 26. And it's not. Ben, the vinegar she tested is more concentrated than the others. So, if you're trying to neutralise some vinegar and it's concentrated, you will need more alkali, which is the sodium hydroxide. Again, it's less than we expect. So Amy and Ben, it doesn't look like they're right. Carl, she made mistakes when she measured the volume of vinegar. So we've got to think, what mistake would she have made to get a lower value than needed? Would she have used too much acid? So too much vinegar in the conical flask, or too little? And we'd have to try and make a decision on that. So we've got to really justify things. This is quite a high level question. Okay, so it wants the best explanation, and then some good reasoning explaining why each person is right or wrong. Then we come to part C. Really nice one. In the reaction, hydrogen ions react with hydroxide ions. Complete the equation for this reaction by filling in the boxes. So all I've got to do, choose 3 from here, fill it in. Okay, we've gone through this in class, so it should be fairly straightforward. I mean, I think even in the paper before it's told you that hydrogen ions are H+. So use that information if it's there. Next, magnesium sulfate is used in some medicines. Magnesium sulfate can be made by reacting magnesium oxide with sulfuric acid. Table shows the relative formula masses. Okay, so we're dealing with relative formula mass of some compounds involved in the reaction. So we've got MgO, MgSO4, H2O, and it says calculate the mass of sulfuric acid that reacts with 5 grams of magnesium oxide. Okay, so sulfuric acid. Now we know that it's sulfuric acid, and it's told us a bit in the equation, okay, and in the preamble. And 5 grams of magnesium oxide. So magnesium oxide is this one. So it's 40. The relative formula mass. Okay, so first thing we'd need to do, because we're not given it, is work out the relative formula mass of H2SO4. And then from that, because this is a 1-to-1 ratio, we would want to find that ratio. So we'll get that value, and then how much of that would react with 5 grams of magnesium oxide. Okay, so you'll have to work out how that happens. Ellie works out a formula for calculating the maximum mass of magnesium sulfate that can be made from different amounts of magnesium oxide. Right, Ellie's formula is mass of magnesium sulfate in grams equals 3 times the mass of magnesium oxide in grams. Use the equation and information from the table to explain how Ellie's formula works. So if we look at the information from the table, well, we've got 120 here and 40 here, so that should be a clue as to the 3 times. Okay, and then we've just got to really express that in words. Okay, so use these values and express it in words, and then we're pretty much done. And that's the end of that one.